So good morning, team. Good morning, team. My name is Teacher Wanata Rubinga, and I come again this day to share with you some of the concepts spoken about in computer networking field. So today I've chosen a topic. I find happiness in sharing these topics because I'm involved in teaching, in lecturing, in corporate training, call it. So I find happiness in sharing, right? So today I've come up with a topic which is a comparison between a LAN and a WAN. So I'll be doing a practical presentation in packet tracer and logical workspace. I think those who are familiar with the packet tracer, they know what I'm talking about. So I'll be dragging in components, devices into the packet tracer workspace and explaining as we go the differences between LAN and WAN. Okay, it is going to be interactive, really. Okay, so without wasting time, okay, a LAN stands for local area network, and it is a network that is small in size and does not cover a very large geographical area, and it's owned by a single authority or entity, if you want to call it, or organization, and it's managed by a single network administrator. So okay, so those are the points we are going to be looking at as we construct the diagrammatic understanding of a LAN compared to a WAN. Okay, so what are the building blocks of a LAN? In order to come up with a LAN, we need devices. We need endpoint devices. Okay. So remember, for a computer network to exist, we need a source point and a destination point. And in between, we need intermediary devices or networking devices. Intermediary devices, which are going to read addresses and make forwarding decisions. From source to destination, they read addresses. Remember, when a packet is released from a source point going to the destination, it carries 3 addresses, I can say. It carries 3 addresses, namely, it has got a port address, then it has also an IP address and a MAC address. So we have the intermediary devices, which act as postmen to read the address and direct the packet towards the destination point in the internetwork. So this is it. So we have got the source point, which is going to attach or to encapsulate those addresses onto the packet that would have been created. So there is source and destination address, source and destination address, and source and destination address. The destination addresses are read by the intermediary devices, and they use that as guideline to forward the traffic towards the destination point. Okay, so there we are. We have got our source devices, PC1, PC2, PC3. Okay, this is PC3, PC4, and PC5. Okay, then I choose another device. This is now going to be the intermediary device, the local post office, the local post office, and in the name of a switch. So we have got a switch, and I'm going to choose 2960 switch. There it is. I drop it in the logical workspace. So by the way, this is logical, right? But we'll find another day where we can now come up with a physical view of this logical workspace, okay? This discussion is meant for network engineering enthusiasts. those who are interested in network engineering, right? Those are interested in network engineering, the entry level to the intermediate levels. Yes, I'll come up with another lesson for the advanced levels, right? So, okay, fine. There we are. I connect these pieces to the switch. Okay, so I've chosen a cable, and this cable is a straight through cable. So I click my first PC, which is PC number 3, and then I go to the fast Ethernet. Remember, fast Ethernet operates at 100 Mbps is transfer speed. So fast Ethernet, and it's limited to 100 meters of length, of a segment length. If we increase above that, then our signals will be susceptible or vulnerable to signal attenuation, which results in signal loss. Okay, so we need to limit to 100 meters in each and every segment, each and every connection that we have. Okay, so what is the next port to connect to? It's FA0/2. Can you see I'm doing it systematically? We need to choose ports as they come. Of course, yes, I can randomly choose. I could have chosen maybe port label 17, but for good practice, we go incrementally. We one in that order, incrementing order, one at a time. Okay, fine. So FA02, fast Ethernet is 100 Mbps. You need to know that. Okay. We go to PC number 5. We're going to choose the port. Okay. Port is FA0, fast Ethernet 0, 2, 3 there. Okay. So what we have done there is to create a LAN. We've already created a LAN, which is made up of 3 computers and a switch. If these computers, if PC number 3 has got communication to PC number 4, it passes through the intermediary device, which is a switch. So that is a switch, which can be given a host name, by the way, which can be given a host name. So I will give it a host name. I'll say first floor switch. So this is a first floor switch. Giving it a name, right? So we come to the PC, first PC, which is PC number 3. We give it an IP address. Okay, 192.168.1.1. Okay, so that's an IP address which has got a subnet mask, which has got a what? A subnet mask, which is 255.255.255.0. All right. So what are we saying about this? It is an IP. Okay. What is the other one? It is the subnet. I will explain what an IP address is and the subnet mask as well, what it is. An IP address is a unique logical address used to identify a network device. A logical address used to identify a network device. So which means an IP address should never be duplicated. It should not be duplicated or repeated. That will cause a conflict. And the 2 devices affected will not be able to communicate or to participate in the events of the network. So what are we saying there? It has got to be unique. What you see there is an IP address with 4 octets. With what? 4 octets. So the first octet is 192, separated from the second octet by a dot. So we have 192.168.1.1, 4 octets, and Below, we have a subnet mask, which is 255.255.255.0. What does 255 mean? It means it is masking the first 255 is masking the first octet of the IP address, which is 192. And what it means is 192 is a network portion. We've got a subnet mask there with 255s. So where the positions where we see 255s, it means those positions are masking octets of the IP address, and those octets should be logged to be network portion. So what we see there is 192.168.1 are network portions, are network portion. Those octets are network portion part of the IP address. Why? Because of the 255.255.255. So we've got the three subnets, three octets, which are network portion because of the three 255s. What about the last one, which is masked by a 0? It means it's a worst portion. It is a worst portion. Are we together? It's a discussion, by the way, yeah? It's not a lesson. Please, it's not a lesson. I'm discussing with you guys. To those who are interested, you can be able to gain 1 or 2 points. Those who are doing the course, diploma, the degrees, even masters, you can come in, join, and then we discuss together. I can check out your comments to see where you want us, the direction you want us to take as well. So it's a discussion. This is a free discussion, yeah? Not a lesson. It is not a lesson, okay? Listen to me. So there we are. We have got the subnet mask. So a subnet mask is a guideline. It shows to us. It's a marker that shows to us which parts of an IP address are the network portion, and which ones are the what? The host portion. Okay. So in the given example, we've got the 3 octets which make up the network portion, and 1 octet, the last one, which is a host portion. Let's see how it goes. Okay, fine. I'm done with that one. It was a demo. So we go to the second PC. It gets also an IP address. So I would want to get an explanation from you to say, if it is a network portion, then what is the behavior when we are addressing the other PCs? What should we do about the network portion? Should it repeat? Should it repeat? I'm asking. The answer is yes, it should repeat. Why? Because it's masked from change. It does not change because of the 3 255s. So there we are, 192.168.1. Now, check. We have finished up the network portion. We are now coming to the host portion. And I said, I've alluded to it already, that a host portion should be unique, to avoid address duplication. So there we are. We started off as 1. Now it comes on to 2. Subnet mask does not change. The subnet mask does not change. There we are. We move on to the third PC. What is the address? Can someone say it? I can hear. I can hear. What is the address there? It's 192.168. Let's go. Finish it up. .1, yes, because it's network portion, it does not change. And then for it to be unique, it has got to be either a 3 or a 4 or a 5. Doesn't matter the order, right? It can be 100. By the way, these addresses, they start from a 0 to 255. That is our number range. 0 all the way to 255. So if I had written 256 right there, it was not going to be a correct IP address because our upper limit is 255. Are we together? But for good practice sake, we are following in order. 1, 2, and then this becomes what? 3. But however, we can go all the way up to 255. No 256, no 257. Are we together, guys? There we are, 255. Dot 255. Dot 255. Dot 0. Can you see that? Yes. So we have completed the labeling. We are not configuring addresses, but it's label. Remember, when we are configuring, we need to be guided by the labels. Yeah? This is this is now part of a documentation. It will be a documentation. We can have a printout of this, or we can have a soft copy stored somewhere in a safe place of this for future reference. Remember, we are guided by a configuration policy, organizational configuration policy, whereby all the configurations have got to be documented and managed by change management, and so that we avoid configuration drifting. Configuration drifting away from what was planned and saved. You get what I mean? So it's a good practice in engineering, in computer network engineering, to have a documentation kept so that if hands change, if engineers change, still the configuration, people have got somewhere to refer to know how the devices or the systems were configured. So we need to stick to the configuration documentation so that we reduce cases of configuration drifting. Are you with me? What is the drift? To move away. So we don't want to move away from the initial configurations, which are known to be working. Which are known to be working. So this is I could use another word called another term called configuration baseline. A configuration baseline. So let's stick to the configuration baseline. Is documented and kept in our storage. In our archives for future references. For future references. Remember, everything is stipulated by the policy, configuration policy, which is formulated by the managers, and everyone is going to be guided by that policy. Thank you. So what we have done there, 3 pieces making up a small LAN. But however, this LAN can expand depending on new users. Remember, in organization, what we call onboarding. Someone has been onboarded by the HR department. So that's a new user. You would need to create to connect more computers according to new users coming in or onboarded into the organization. Okay. So which means this port, as you can see, the switch has got multiple ports. It has got 24 ports. So it ends at 24 ports, which means it's not as scalable enough as we would want. It's not as scalable enough as we would want. So which means now if we anticipate the organization to grow, to expand much faster, then we need to change the devices that we set up. We need to go 48. We can go to 128. Those devices with higher port densities. Devices with higher port density. So this is a 24 port density. But however, listen to this. If you want to expand this network with the 24 port, still you can. How? By redundantly connecting multiple switches. So I could have a choice here where I can have another switch and another switch, 4 of them expanding. So I would have, like, for example, if I had set up another 4 switches, that would mean that my ports are going to add up to 24 by 4, which is 48, 96. So we have a 96 port LAN. Are you with me there? 96 port LAN. That's another way. What is the alternative way? We can have one combo device or one big device I could call it a modular device, which means there are big switches out there which are called modular switches, which have got line cards. You can slide in line cards to expand the port density. So it's one unit, one switch unit that has got line cards in which you can decide to expand the port density to include multiple ports to support multiple users as well. So there are different ways to achieve scalability. There are different ways to achieve scalability. So that's a term, eh? It's a good term. It's a good word. It's an industry jargon, by the way. Scalability, it means ease of expansion. Ease of expansion. So networks should be, so what is the encouragement here? Networks should be planned, designed to support scalability and fault tolerance. Fault tolerance, okay? And eliminate single point of failures. Single point of failures. Okay, fine. So this is a simple LAN. There it is. And the switch also can be given an IP address. Let me also include the address for the switch right there. Why do we IP address a switch? Good question. Why do we IP address a switch? We address a switch for good reasons, because we want the switch to be managed. So there are two types of switches, guys. There is the plug and play. Plug and play. You just connect a switch and we are now able to use it without configuring it. Usage without configuration. That's one way. Another one is you power it on, then you customize it according to organizational settings. Remember, we spoke about configuration baseline. So these are some of the things whereby we need to configure this switch according to the configuration settings, which are known and stored, and then we maintain that and not run risk of a configuration drift. Okay, fine. So what is the address that we can give there? We have used 1, 2, 3, and then we can go to 4. All these pieces are in the same network segment or same LAN, if you want. Same network segment or LAN. Okay. So 3 taken, 4 can be used. And what is this address? It's for management purposes. It is for management purposes. What is to manage? To manage is to configure, right? To configure a switch with settings that are organizationally accepted. Are we together there? Right. I'm not serious. I'm not serious. I'm not serious. Okay. Okay. I hope someone is following up. So what do you need? You need Packet Tracer. You can download Packet Tracer from Network Academy, NetAcad. So just create an account there, then you get in, the resource is there, you can download it to your PC and be able to use it. Okay, fine. So fine, then now we have created a simple LAN. Let me label it as LAN 1. So this is LAN 1. What are the characteristics? PC is connected to a switch. Okay. Communication is kept localized, does not go out. As we can see, 3 pieces, of course, they can be added up to 24 in this case. But however, if you want to expand this network segment, you can add another switch and another switch and another switch to create a one big network segment. Are we together there? So there we are. But remember, communications are not only, they are not forever going to stay local. They need to go outside, outward communication to other networks, Are you with me there? communication, yes, fine, it can be needed within, but it can also be outbound. Right, let me go. There is another point which I need to highlight. This network is a work group because we don't have a server. We do not have a server. So there are two types of networks, a work group whereby services are shared equally among the devices connected in a network segment. But however, you can have another way, which is all these pieces can now be supported by a server, which is also connected to the switch. And and the server is there to give a service, a dedicated service to the client. So it becomes a client and server situation. Client and server situation. Are we together there? Do you get me? Do you get? I'm not serious. It's smooth flowing. We don't, no, for education to happen, for education transfer, you don't need to be serious. Be relaxed, right? As I take you through. Remember, I said I'm sharing. It's a share. I'm giving you a share, right? Right, there we are. So now, for the packets to move out of this network segment to another network segment. So we can have multiple network segments, by the way, in one LAN. Remember, we say the LAN can be a network that is managed by a single authority or organization. So for packets or frames, okay, I would want to call them frames. So we have what, can you write this down? Frame and a packet, they are two different things. Frames are known to be the protocol data unit, or the frame, or the message type. Okay, what can I say? The message type at layer number 2. So we have got layers, guys. We have got layers. We're talking about layers there. So we have got layer 1, layer 2, layer 3, layer 4, layer 5, layer 6, and layer number 7. It's called OSI 7 layer model. It's called OSI 7 layer what? Model. You see the cables. The cables, they operate at layer number 1, which is electrical signal, right? Line coding. If you use the cables, we are transporting or transmitting an electrical signal. So that is a layer number 1 functionality. Code it to electrical, and code it to fiber optic, and code it to wireless. That is layer number 1. So any media type that you know about, it is operating at layer number 1 of the OSI model. Okay. Then we come to layer number 2, the switch that we have included there. It's a layer number 2 device. Are you with me there? It's a layer number 2 device, which means at layer 2. So, okay, at layer number 1, no addressing at all. Then layer number 2, we have got an address. That is a MAC address. That is a what? A MAC address. So let me write it here. In this LAN segment, as the switch makes forwarding decision between the devices communicating, then it uses MAC addresses. It uses MAC addresses. You need to know this, very important. It uses MAC addresses. That's a switch for you, right? To make a forwarding decision, which means a switch has got a MAC address table, MAC addresses in the MAC address table, in the MAC address table. Okay, very important to know. So there is a MAC address table. So that's layer 2. So if you are asked in any exam, the kind of a table that is used to make forwarding decisions at layer number 2, it's called a MAC address table. And what is in the MAC address table? These are MAC addresses. These are what? MAC addresses. Is the point been taken? MAC addresses. How do we view the MAC address table? It's viewable, by the way. We get into the switch and then we run show MAC address table. Show MAC address table. then it comes out in terms of ports and the MAC address, port and the MAC address of all these three devices connected. We are going to show that in our subsequent discussions, in our subsequent sharings, okay? So now for information, okay, for traffic, I'll call it traffic, or for frames. So what did we say, guys? Switch forwards frames. Yeah, switch forwards so a switch forwards frames. And we say the frames are synonymous with layer number 2. Okay, that is very important to know as we move. All right. And it's layer number 2, which is data link layer. Layer number 2 is data link layer. So which means a LAN segment is synonymous with LANs associated with, in terms of decision making, in terms of decision making, LANs, they refer to the data link. Data link. Okay, let me write it here. Switches operate at data link. Switches operate at data link layer of the OSI 7-layer model. You need to keep this OSI 7-layer model. That's a switch for you. So a switch limits itself to layer number 2. Are you with me there? We are talking about layer number 2 switch in order to talk about a local area network. Then let's move. Now, information, okay, packets of, okay, frames. I'm limiting myself to frames. Frames, sometimes they need to move out of a network segment as they are destined for other network segments, which are not here, which are not within. So now we need now to talk about a device, which we call a router. Which you call what? A router. So I'm gonna drop in a router right there. That is a router for you. And this router is going to be connected to the switch. They don't fly. Frames do not fly wirelessly when it is a wired device. Are you with me? You need to know the type of medium that you are using. Here, there is no wireless. These are wired devices. So we need to have a cable. So which type of a cable? It's a copper straight through again. So I connect my copper straight through on FA0/4 all the way to the router on a gigabit Ethernet 0/0. Are you with me there? So there we are. We have got a device, which we refer to it as a router. And this device, so I would want to give it a name. This is a college network. That is a college network. So I'll call it a college router, college A router. Router. Right. So that is our router. And this router, guys, is now a device that is now going to connect us to other network segments. So good statement there reads. A router is a device that is operating at layer 3 of OSI model. And that layer is known as network layer. Network layer. To move packets, can you check now? I've changed my word. I started off with the frames when I was in the LAN. now on the switch. Now that I'm on the router, we now make use of this word called packets. So a router forwards packets from a network segment into another network segment. So quickly, I can have another network segment there. I can have another network segment just to demonstrate that. So I want you to keep track. Look at the word router. So router is like a noun that is got a verb which is routing. So if I talk about routing, I'm saying it's now the ability for a router to receive a packet, reads its destination IP address and forwards to the destination network segment. Are you with me there? Clap hands for me. So a router is simply a device that operates at layer number 3, which reads, yes, both MAC addresses, but it does not end there. It also goes on to the IP address. It reads a header file called IP header file to understand the destination IP address of the packet, and forwards to it. What about a switch? A switch is localized. It's working within a network segment, but a router is there. It connects network segments. A router connects network segments. Are you with me? Yeah. Right, there we are. We go to cables, want to do the connection, want to connect our router to where? Can you see something again? The router is a device that has got limited ports. Look, if I take this gigabit Ethernet 0/1, which is left, then we have run out of ports. So a router by design, it has got limited ports compared to the switch. A switch, how many ports did it have? By default, by the way, it had 24, but a router had only 2. But however, we can add more ports on the router. If we wanted to have more LANs, we can add more ports. We can add what? More ports. But a router is not designed to always to add more ports and add more ports. No, like these LAN ports. There is another workaround on that, which is called VLANs. Which is called what? VLANs. So instead of having individual what? LAN segments like LAN 1, here I'm going to come up with LAN 2. And if you want to have LAN 3, then LAN 3 now, what we can do is to do segmentation of our VLANs. Network segmentation based on VLANs. Network segmentation based on VLANs. Are you with me? We'll talk about VLANs as well. It's a package. It's a train, guys, of topics coming to you. Okay, so there we are. I've chosen gigabit Ethernet 0/0. Which is okay. And then I connect to FA 0/1. But it's a good practice to use the gigabit. Because remember, this is a link that we want to be fast enough to transport between a switch and a router. So I would rather, good practice to use gigabit Ethernet. Are you with me? So giga, in terms of transfer speed, is faster than fast Ethernet. Point taken. Then we can have our PCs as well. Just one for demonstration. Okay. There we are. Good. So you see, let's go to LAN 1. We've got 24 ports, which translates to 24 pieces. All of them racing, competing to use the available link, which is the one that connecting to the gigabit to the router. So which means there is multiplexing there. There is what? Signal or frame multiplexing. Using time division multiplexing, time division. One frame separated from another based on time. They are multiplexed and they move serially in a serial format. Single file format. So which means therefore calls for higher bandwidth on this link. Higher bandwidth on the link between a switch and the router. I'm supporting the point to say, because we've got multiple devices, all of them sending simultaneously to the router for upward communication, then we need to make sure that that link does not become a what? A bottleneck. We need to free up space there by choosing devices with higher bandwidth. So we could use a gigabit Ethernet, or we could choose a switch with a higher bandwidth, like 10 gigabit Ethernet port or 40 gigabit. Now it depends with the environment. This is just a simple home office, small office. But if it is a data center, for example, we would now need to use fabric switches. These are quite capable switches to now connect, because they are now transmitting or transferring data at 40 gigabits per second, 100 gigabits per second, and they are using fiber optic, fiber optic ports and cables to connect to the router. The router also becomes a what? A fabric device, so that everything becomes a gigabit network. Everything can now become 10 gigabit Ethernet, 10 gigabit network, or 100 gigabit network. This is found in the data centers and ISPs and the cloud computing. But if it's for small office, home office, small companies, small enterprise companies, we don't need higher bandwidth. Are you with me, class? You're not class. You're my good friends. You're my friends. Right, there we are. So this is what has happened. We've created a what? A LAN that is connected to the router. But I want you to take note. Let me enable. You see this port, which is in a red there with a red triangle, it's not labeled. It does not show the port label. So we want to enable port labeling. We want to enable port labeling so that we see which port we have connected to. Always show port labels in logical workspace. What is the logical workspace? This space where we are dragging our devices into, it's called logical workspace. So we've highlighted or ticked the box that says show the port labels. Thank you. So I close that one. So now we see gigabit Ethernet 0/0, so that we stand guided in terms of reference. Now if we are now configuring those ports. Another point before we run away from there is to say this port, gigabit Ethernet 0/0, is a LAN port. It is a LAN port. And this one again is also a LAN port. What does that mean? It's a LAN port. Can I add another point? It's also a default gateway for LAN number 1. If we are talking about G0/0, it is the default gateway for LAN number 1. It is LAN and default gateway for LAN number 1. What does that mean? A gateway, default. Default, it means there is no other way out of. So the only way out is that G0/0. Yes, the word default, a gateway out of the network. Are you with me? For LAN number 1. So which means every LAN segment connected to the router has got its default gateway. So here, if you look at router, college A router, it has got 2 default gateways. One for LAN number 1 and another one for LAN number 2. Do you get the point? Okay, everything in caps, by the way. LAN number 2. So we have LAN number 1 and LAN number 2. Another point, a very major one, which I had forgotten about. Being LAN and private. So this is a private network. It's a what? Private network. Protected from the view of the outside. So it's private. If it's a private network, it therefore means it has got to use private IP addresses. It has got to use what? Private IP addresses. And it's owned by which organization? College A organization. And in the organization, we have a network administrator who is responsible for making sure that what happens here is controlled by him or by the college's policy and not shareable to the outside world. So a router becomes our perimeter device. It becomes our what? Our perimeter device. We can have this router as an integrated router with security as well, whereby we got the firewall services running so that we can now allow for filtering of traffic. Not unwanted traffic cannot pass through, or wanted traffic can pass through. We can also configure what are called the access control list on this router so that it filters traffic based on where it's coming from and also where it is going in terms of addresses. In terms of address, it looks like I'm going deeper, man. I'm going deeper. Yes. There it is. It can be, a router can be used for security purposes. Same as the switch. A switch can also be used for security purposes, whereby you can allow a device to connect to the switch based on its MAC address, based on its what? So which means the switch can do MAC address filtering. It can do MAC address what? Filtering. Then a router also can do IP address filtering. Remember, we say the switch reads MAC addresses. A router reads IP addresses for decision-making purposes. So a router, because it uses IP addresses, we can configure it to filter out, filter in, filter out, allow, disallow certain IP addresses, entry into sensitive network segments. Are you with me? By what are called access control list. By what are called what? Access control list. That's security. So that's another layer, which we'll look at. God permits. If God permits, we're going to go there. But a switch uses what is called switch port security when it applies security based on MAC address filtering. On what? MAC address filtering. I think, guys, if you are quick to refer to our previous, just what we've just talked about or discussed, switch is a layer 2. It works on MAC addresses. So switch port security is simply MAC address filtering, which is a layer number 2 security approach. Then a router is a layer 3 security approach. What is the address there dominating? IP address. So if a router is able to say, which packet is this, from which network to which network, am I allowed to forward it or deny entry? Then that is the router at layer number 3. We are looking at security. Okay. And the router, we've noticed, it has got very limited ports. Okay. So now, what we want to do is to connect this router to the wide area network. So for simplicity's sake, I'll just choose 1941 router, drop it in. This router is now representing. It's representing. I'm not saying at the ISP, this is the router that they use. No, the ISP, they work with large volumes of what? Of traffic, network traffic. So the routers that you're going to see there are high capable routers. Are you with me? The high capable routers. So what you're gonna do here is just to drop in a router, and then it becomes the representative. It plays the representative of the ISP. But there you're gonna find the MikroTik routers, the Cisco routers, the Juniper routers, the what? Way routers. You know, these are the different players in terms of vendors in the router manufacturing, you know, in the marketplace right now. So Cisco is a player, MikroTik is a player there in there, Juniper is also a player right in there in the ISP environment. Okay. So I'll drag in 2 routers, by the way, 2 routers. One is in this other side of the network and the other on the other remote side of the network. Then how am I going to represent my ISP? I'm going to draw a line, a circular line, a circle diagram. Right, there we are. There we are. Okay. There we are. We have got this line. I had made a mistake, a smaller line. You can ignore that one. So the bigger line is now representing a what? An ISP. Okay. So we close this. Then let me see if I can remove the smaller thing there. Yes. There. Delete it. There it goes away. Right. Then I undo my delete. I think I see. I think you see what I'm doing there. If I want to undo a previous action, I click here. If I want to delete, I click there. If I want to label, I click right there. If I want to come up with these diagrams, I click right there. It depends. If you want it in a circular form, in a clipped format, you draw this one. Then if you want it in a rectangular format, the same diagram in a rectangular format, you click that one. If you want it in a free form, you click that one as well. Then draw a line. If you want a line, that one. If you want to undo your previous action, like you want to bring back the small thing that I had deleted, it's not coming up, but you would use this backward arrow and forward arrow. If you want to enlarge and shrink your what your workspace, we use this magnifier. Are we together there? Too magnified. Reduce it. Right, there we are. So what do we have? We have a LAN. Then on this router, our boundary router or our perimeter router, we need to connect it to the ISP. But now, to be able to do that, we need to have a one port. We need to have a what? A one port. And this one port, let me look for it. So I'm going to click my router. Okay, it's fine. It's not clicking. It's not clicking. So what we would need there is a one port that connects to the other one port on the what? On the ISP side. So we need, remember, that was a LAN port, and then we need a one port to connect on the wide area network. So the ISP, as we can see there, this is ISP. Hey, we can call it ISP. Hey, we have used BC ISP. Give it ISP A. Right. This ISP A, what is happening inside there? Okay, before we go to what is happening inside, let's analyze this router. This router is called an edge router. It's called an edge router. Why edge? Because it's found at the edge of the network. At the edge of the network. This router has got a major role to play. It is the one that receives from multiple users. Remember, this is just one router representing college A. We can have another one representing company B connected to the ISP edge router. We can have multiple for that reason, which means this what? This router is an aggregation point. It is an aggregation point, meaning multiple user traffic is coming and converging. So it's a convergence point, converging into this edge router. This edge router is present on a special position of an ISP network called point of presence. Point of presence, POP. It's called point of presence. It is there to provide reachability of users into the core network of the ISP. So what is this one? It's ISP core network. ISP core network. Okay. What do we find there? We find service provider router. Service provider router. Routers. They're all in there. And can you see this network can be expanded and contracted? But what is the goal? What is the objective or the mission of an ISP? Is to expand it and cover as much area as possible in a nation or in a continent. Because the more the area covered, the more the customers are going to connect. Subscribers, we call them subscribers. And also at the aggregation point, what do we see happening right there? At the aggregation point, we see authentication. We see authentication, okay? Users are going to be authenticated. So there is user access control. User access control in terms of using a server, AAA server. Authenticate, authorize, and account, AAA server. So AAA stands for authentication, authorization, and account, which is user verification. User need to be verified in terms of whether they've got an account in the ISP to access the ISP network or services. What do we have there? The ability to reach web services like Google, Facebook, YouTube, Yahoo, cloud, Microsoft. Remember, Microsoft is bringing in everything as a service, anything as a service, software as a service, database as a service, platform as a service, infrastructure as a service. Everything is coming. But now for you to be able to access those things from the college, you need now to be connected to the ISP. And you need to be connected to the ISP. There's a need for connection to the ISP. So for you to connect, you need to have created an account, signed up. You have an account that is paid up. So you're a subscriber. You subscribe, and it's based on monthly, quarterly, or annually for you now to access the services provided by the ISP. If ISP does not have the services, this ISP knows where to get the services. It would now uplink to other ISPs. Are we together there? So that they form a network of ISPs out there in the one. So what is this now? If now we connect, so which means we can have something is not happening here. So we can have multiple LANs, right? Let me take in another router, drop it there, another switch right there. Then we have a PC, Okay, I'm just showing, this is a remote network. That is a remote network. And what do we have there? We have this PC7 communicating with the PC3. So, okay, fine, I'll do my cabling. So it's simply going to repeat what I had earlier done, what I've earlier done on the other side. Okay, all right. Okay, the PC to the switch. All right. Then another cable, switch. Remember, we said you need to make use of the gigabit. Okay. Then okay, if you look at this router has got two blank openings. Can you see the two blank openings? You see, okay, let me zoom in. I've zoomed in for visual clarity. If you look at those ports, there is G0/0 and G0/1. These are the ports that we have already used up. Remember, we're talking about bandwidth utilization, higher bandwidth, the better. But we have those two openings, which means we can slide in or install cards. We can install what? Cards. So that's one connection that we were looking for. By default, it's not there. So we need to install it. We would need to install it. In order to install it, we would need now to switch off the router, first and foremost, then come here and take our what? Our card, come, slot it in. Then we switch on our device. Device is switched on. Okay. So you see, if you try to take out a module when the device is switched on, then it says cannot remove a module when the power is on, which therefore means it's not a hot swappable module. I think someone has gotten me. Hot swappable module, which means a hot swappable module is a module that you can, a module blade that you can take out while the device is running, and there won't be any conflict in terms of the electronic and electrical mechanics of that device. Are you with me there? So so now, for you to take out, you need to switch it off. For you to install, you also need to switch off, then back on. Good one. So it's done. Then we come to the other router. We also switch it off. Let's try to add while it's on. Cannot add a module when the power is on. Well understood. Power it off. Okay, there we are. Power it on before we exit. Sharp. Then we come there again. Off. Someone might have a question. They say, why are you concentrating on the right side? Why not the left side? Sure, we can get it. We can what? Take it out first and then install. Sure, we can. No problem. Right, so we are sorted there. We are sorted. This one also need a card, a one card. Does not have. So a router by default does not have until you install. Okay. Very important point. Yeah. But it depends with the type of a router. That is another point. It depends with the model of the router. Some models come with pre-installed cards, WAN cards. Some do not. So when you do your procurement, you are setting up, you have designed a network, you're setting up, you need to make a research of these devices to know which modules come pre-installed, which ones are not there, and in terms of compatibility, what do you need? So that's feasibility study. You need to carry out your physical feasibility against your financial feasibility. Thank you. So there we are. I've taken this one, which is serial DCE. That's the one that I've taken with the clock. The clocking side is always present it's connected on the ISP side. So serial 0/0, I connect to my router on serial 0/0 or 0/1, whichever you want. Right, there we are. Right, I take again another one, the clocking side on the ISP, that's serial 00 or serial 01, doesn't matter. Please, it does not matter. Right, as long as it's a serial port you have chosen. So there we are. So what do we have? We have our LANs have now been connected to the ISP, and the ISP, okay, aggregation point. There is a G there which is left. All right. And the ISP, the device is going to connect to the POP router called edge router. And then now we are going to see right there the POP. Before the packets move deep inside the core network, we see authentication, authorization, and accounting. As users are controlled in terms of the access to resources in the ISP. And there is a server there, AAA server, which can be a Radius server or a TACAX server. These are two services that are coming in for authentication there. And then we said the ISP makes use, it's a public space. It is a what? Public space. Let me write a search. ISP is a public space. You need to know this. So it uses public IP addresses. ISP uses public IP addresses. Remember, we say the private IP address when we on the LAN. Now, at the ISP side, we have public IP addresses. So what is happening here? Someone is confused, I know. So a packet comes in, it is stamped with the what? With the private IP address. The router routes to say, what is the destination IP? The destination IP is right there also. So there is source and destination. What are the two addresses carried in the packet? Source and destination. Then the router is going to say now, but in the public network, we don't use private IP address. So I'm going to translate the private IP into a public IP address, which means ISP would have given college A public IP, which is right there on the one port. Can have a public IP address right there. And on this router, we have a protocol. Okay, yeah, let's call it a protocol called NAT. NAT, which stands for Network Address Translation. NAT stands for N for network, A for address, and then T for translation. So what is going to happen with this router? It's a NAT router, that one. That stamp, that field with source IP is going to be changed from .1 to a public IP address that would have been given by the ISP, public. There is a B left there, which would have been assigned by the ISP to this LAN network or college A network, would have been given a public IP address to translate to. Are you with me? To translate to. So So what are we going to see happening to the packet? The private IP address is erased or replaced. It's going to be replaced with a public IP. So the packet, if it goes from this point, it is now a different IP address. It's no longer the former private. It is now the public IP. It is routed along in the core network of the ISP. And at this point, you see that edge router on the other side, it is going to translate back. So which means this one also, again, it's a NAT router. Also a NAT router to translate the public IP address back to private IP addresses, because this is a private LAN, so it uses private IP addresses. So do you see how our network is in private? The translation, the repeated translation of addresses from source to destination. It started off as a private, but it's very important to say, when the translation happens on the first router, then a record of the translation is kept in a table, and the table is called the NAT table. Hey, it looks like I'm going deeper. I'm going deeper. Go deeper. All right, I'm going deeper, right? So I can't control the edge to want to dive deep, okay? So when the NAT translation happens, there is a table that is created to keep a record of the translation, so that when it is now a backward communication, the router will simply refer to the table and say, okay, what was my previous translation? I translated from this to that. Then how am I going to translate back? I'll simply use this IP address, then it translate, so that the packet can now be delivered to the correct destination point. Remember, in a web communication, there is a web server and a web client. Maybe this is a web client, Google Gmail web client with a request to the Gmail server, and then the Gmail server is giving back a response. Are you with me? So that is an established communication. It is an established communication. So we need to keep track of the translations, IP address translations, so that devices do not make mistakes in translating back to their former states. Are we together there? Okay. So ISPs are there to help us to create WANs. What is WAN, by the way? WAN stands for Wide Area Network. So this is a LAN, a remote LAN. I'll call it a remote LAN. How is it remote? With reference to the LAN number one. With reference to LAN number one, we have been able to successfully send a message to remote LAN PC, and then who has enabled us to do that? It's an ISP. Listen, so an ISP is a company, yeah? An ISP is a company that has invested a lot of money to to plan and implement routers and switches in this network, which spans or which covers the whole country, for example, or the whole continent. And then it depends. There are different ISPs in different nations. Like, for example, in South Africa, we can talk about Vodacom, Telkom, Rain, different, multiple of them. Then in different countries, we hear a lot of, in Zimbabwe, we have Liquid, we have PowerTel, we've got Net1, and many other. There is Dandem Tande as well, that one, and multiple of them. Okay, so these are companies who have invested a lot of money to create these networks, core networks, and They are now waiting for subscribers to come and register with them so that the users are able to communicate on a wide area network. So what differentiates these ISPs is the uptime, availability time, to say, do they suffer disruptions like power, signal loss due to disconnections? So this is now what measures the qualitative approach, which now differentiates these ISPs. Some are, it's difficult to maintain 100% uptime, but uptime is measured in terms of the number of nines, 99.99999. The more the nines we have, the better the service provider is. Are you with me? The uptime is measured by 99.999, whereby the number of nines after the comma would indicate the reliability. Because it is known that, or said that, there is no network which is 100% perfect. It is bound, prone, vulnerable to disruptions, either internal disruptions or external disruptions. Are we together there, guys? So that's one LAN and another LAN connected together by a WAN using edge routers and series of ISP core network routers. And these routers are going to be routing to each other using protocols such as EIGRP, OSPF, MPLS, and then the edge routers. We can have a boundary router that connects to other ISPs, and it uses a unique protocol called the BGP, Border Gateway Protocol. Border Gateway Protocol to connect ISP A to ISP B. So they can use BGP for ISP intercommunication. But if it is a LAN to an edge router, they don't use a routing protocol. They use static routing. They use what? Static routing. Why? Because static routing does not send routing updates between routers. There is no routing update messages being exchanged between the two routers, which have got static route. So it's always recommended to use default static route. So we configure on college A router, we configure a default static route pointing to ISP. Then the dynamic routing information exchange happens among the ISP routers. It happens among the ISP routers. Guys, let me end here. We'll meet again. Thank you.